Welcome back to Key Safety Talks. Today, we're going to be tackling a subject that might not be the most exciting,
Hmm.
but is super important for any safety pro who, wants to really be at the top of their game.
And that is
Math.
math. You got it. We're going to be looking at a safety professional's reference and study guide and really exploring the math concepts that are essential for, keeping people safe out there.
Now, I know some of you might be thinking math, really. I mean, isn't safety more about regulations and hazard ID and stuff?
Right.
But believe me, there's a whole world of numbers hiding behind all those safety protocols and procedures we use.
Absolutely. Whether you're, calculating risk or designing a fall protection system or just trying to make sense of all that technical data that we have to deal with, math is really the language behind all of it.
It really is. We're going to uncover how all these kind of abstract mathematical concepts actually translate into real-world safety practices.
Yeah.
And who knows, maybe we'll even have some aha moments along the way.
Oh, I'm sure we will. Let's kick things off with something that can trip up even the most seasoned professionals.
Okay.
Order of operations.
Oh, yeah.
PEMDAS.
PEMDAS.
Parentheses, exponents, multiplication and division from left to right. Addition and subtraction from left to right.
Oh, yeah. I remember struggling with this back in school.
Right.
It just seems so nitpicky.
Right.
But now I realize how crucial it is, especially in safety calculations where the stakes are so high.
Absolutely. Imagine for a second you're trying to calculate the safe load limit for a scaffolding structure.
Okay.
A tiny error in the order of operations could give you a totally different result and, potentially put workers at risk.
Yeah, that's a sobering thought. So PEMDAS isn't just some, arbitrary rule. It's the foundation for accurate calculations, which can literally have life or death implications in our field.
Exactly. And the study guide actually has a great example to highlight this. They use the equation 4 plus bracket negative parenthesis 1 minus 2 parenthesis squared bracket to illustrate how, even a small deviation from PEMDAS can lead to totally different and incorrect results.
Right.
If you follow PEMDAS, you get the correct answer of 3, but if you don't, well, let's just say the consequences could be disastrous.
Yeah, speaking of consequences, I remember reading about that bridge collapse a while back, where investigators traced the root cause back to a miscalculation in the order of operations during the design phase.
Wow.
It's just a tragic reminder that these seemingly small math errors can have massive real-world impacts.
Yeah, it really underscores the importance of not being complacent when it comes to math.
Right.
Even something as fundamental as PEMDAS can have, profound implications for safety.
All right, let's move on to another fundamental concept,
Yeah.
positive and negative numbers.
Right.
Now, this might seem basic,
Right.
but it's more than just getting the sign right. It's about understanding what those numbers actually mean in a safety context.
Yeah, in safety, a negative sign could indicate, a decrease in pressure, a change in direction, or even a force acting in the opposite direction.
Exactly. For example, the guide points out that positive multiplied or divided by a negative equals a negative.
Right.
Now, that might seem like a pretty simple rule,
Yeah.
but imagine you're calculating the impact force of a decelerating vehicle during a crash investigation.
Oh, yeah.
A sign error there could totally throw off your analysis and lead to incorrect conclusions.
Absolutely. It's not just about, crunching the numbers. It's about understanding what those numbers represent and how they connect to what's happening in the real world.
For sure, and sometimes those positive and negative signs can be the difference between a safe system and a potential disaster. I remember a case where a pressure gauge was installed backward.
Oh, wow.
So it was reading positive pressure when it was actually negative.
Oh, no.
Yeah, and it led to a dangerous overpressurization of a system. Luckily, they caught it in time, but it could have been catastrophic.
Yeah, that's a perfect example of how something as seemingly simple as, a plus or minus sign
Right.
can have huge implications.
Absolutely.
It's all about, paying attention to detail,
Yeah.
understanding the context of the calculations we're doing.
All right, let's power up our understanding a little bit here
Okay.
and talk about exponents. I like to think of exponents as mathematical shorthand for repeated multiplication.
Right.
It's a way to express really big or really small numbers in a concise way.
Yeah, and in safety, we often deal with both extremes.
We do.
Think about the massive forces involved in like a structural collapse or the
Yeah.
tiny concentrations of, hazardous substances that can still pose a risk.
Exactly. The guide uses the example of 10 to the power of negative 6,
Right.
which is equal to 0.000001.
Right.
That's how we might express the concentration of, say, a certain chemical in the air.
Right, a seemingly small number, but it could have major implications for worker health, depending on, how toxic that chemical is.
Exactly. It's about appreciating the scale of the numbers we're dealing with and how those numbers translate into real-world hazards.
Absolutely. And that brings us to scientific and engineering notation,
Oh, yeah.
which are kind of like superheroes for taming these really large or, microscopically small numbers.
Right. Scientific notation expresses any number as a product of a number between 1 and 10 and a power of 10. It's super versatile.
Yeah, and engineering notation is similar, but it sticks to exponents that are multiples of 3, often using prefixes like kilo, mega, or micro.
Right.
This is super handy for, practical measurements in fields like engineering and, of course, safety.
Absolutely. So instead of writing out a ridiculously long number like 2,500,000,
Right.
we can express it as 2.5 times 10 to the power of 6 in scientific notation,
Right.
or 2.5 mega in engineering notation.
Exactly. It simplifies things and makes those numbers much more manageable, especially when you're doing calculations or communicating technical information.
And it helps us quickly grasp the order of magnitude, which is crucial in safety.
Right.
Imagine trying to interpret noise level readings or radiation exposure data without scientific or engineering notation.
Yeah, that would be a nightmare.
It would be a nightmare.
These notations provide a standardized way to, represent and communicate these large and small numbers, which reduces the chances of errors and misinterpretations, which is critical in safety.
Absolutely.
Okay.
Okay, let's move on to some concepts that might not be as familiar but are equally important.
Okay.
Absolute values, logarithms, and equation transposition.
All right, starting with absolute values, think of it as stripping away the positive or negative sign of a number.
Okay.
It's about focusing on the magnitude, the pure size of something.
Okay.
The guide points out that this is particularly useful in ventilation calculations,
Right.
where you're concerned with the amount of airflow regardless of the direction.
Exactly. We just care about how much air is being moved, not whether it's flowing in or out.
Right.
Absolute value helps us simplify those calculations.
Yeah, absolutely. Now, logarithms are a bit trickier to explain,
Okay, all right.
but think of them as a way to kind of solve complex equations by relating variables in a different way.
Yeah.
The guide lays out 3 basic rules for working with logarithms. It might seem a bit abstract now, but understanding these rules can be really helpful for, deciphering complex safety data.
Okay, and don't worry, we'll get into some practical applications of logarithms a bit later.
Yeah.
But first, let's talk about equation transposition.
All right.
This is where we get to rearrange formulas to solve for a specific variable.
Right. It's like having a Swiss Army knife of mathematical tools.
Okay.
You can take a formula and manipulate it to get the information you need.
Right, the guide uses the example of the basic ventilation equation, Q equals VA.
Right.
By rearranging the equation, we can solve for any of the variables. Airflow rate, Q velocity, V, or area A, depending on what we're trying to figure out.
Exactly. And this isn't just for academic exercises. Imagine you're trying to determine the safe load limit for a piece of equipment, or calculate the proper ventilation rate for a confined space.
Equation transposition gives us the power to take those formulas from the textbook and apply them to real-world scenarios.
Exactly. It's about, bridging that gap between theory and practice,
Yeah.
which is what safety is all about.
All right, before we move on, let's take a quick step back and talk about something a little more fun.
Okay.
Factorials.
Factorial.
These might seem a bit abstract,
Right.
but trust me, they have their place in safety.
They do factorials denoted by an exclamation mark after a number like 5 exclamation mark.
Yeah.
Tell us how many ways we can arrange a set of things.
Okay.
So 5 factorial means 5 times 4 times 3 times 2 times 1, which equals 120.
Okay.
So there are 120 different ways to arrange 5 objects.
Okay. It might seem like a party trick, but understanding factorials can be surprisingly helpful in risk assessment.
Yeah.
Sometimes we need to figure out the probability of a specific sequence of events occurring.
Exactly. Imagine you're analyzing a system with, multiple components that could fail.
Right. Factorials can help you calculate the probability of those components failing in a specific order, which could be crucial for understanding the overall risk of the system.
It's about recognizing that sometimes the order of events matters just as much as the events themselves.
Absolutely.
Factorials give us a way to quantify those possibilities.
For sure. And speaking of quantifying things, let's not forget about common geometric equations.
Yeah.
Area, distance, volume. These are the building blocks for many safety calculations.
Absolutely. Think about calculating the area of a spill zone,
Right.
the volume of a storage tank, or the distance a projectile could travel.
Yeah, these formulas are essential for making informed decisions in a safety context.
It's about understanding the spatial relationships and dimensions that underpin many safety hazards and control measures.
Exactly. We need to be able to, you know, visualize and quantify those physical realities.
And then there's Euler's number, often represented by the letter E, which might seem like a bit of a mystery. Yeah, it's one of those mathematical constants that pops up in, unexpected places, often in calculations involving exponential growth or decay.
And believe it or not, exponential growth and decay are relevant to a surprising number of safety scenarios.
They are, think about like the spread of a fire or the dispersion of a hazardous gas cloud.
Right.
These phenomena can exhibit exponential behavior, meaning they can escalate very quickly. Euler's number helps us to model and understand those processes.
So understanding Euler's number and its role in exponential functions could help us predict the rate of spread of a fire or the concentration of a gas over time. That's fascinating.
Exactly. It's about using math to anticipate how hazards might evolve and to develop effective strategies to mitigate those risks.
Okay, let's shift gears and talk about something a bit more visual.
Right.
The Pythagorean theorem.
Ah, the Pythagorean theorem.
Now, this might bring back memories of high school geometry class,
Right.
but it's actually an incredibly practical tool in safety.
It is. It's all about the relationship between the sides of a right triangle. A squared plus b squared equals c squared. But it's not just about, finding the missing side of a triangle. It's about understanding how those sides relate to each other in a practical sense.
Right, the guide uses the classic example of a ladder leaning against a wall.
Right.
The ladder itself forms the hypotenuse of a right triangle.
Exactly. Using the Pythagorean theorem, we can make sure that ladder is the right length to safely reach a certain height, making sure it's not too short and not too steep.
And that brings us to trigonometry, which takes our understanding of right triangles to the next level.
Yes.
We're talking about sine, cosine, and tangents.
Don't let the names intimidate you. Trigonometry is all about relating the angles of a right triangle to the length of its sides.
The guide uses the mnemonic SOHCAHTAA to explain these functions. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. It's a simple way to remember those crucial ratios.
Yeah, and those ratios are super useful in safety, especially when we're dealing with forces, angles, and distances.
Right.
Think about calculating the stability of a structure, the force required to lift a load, or the trajectory of a projectile.
It's like having a set of tools for understanding the geometry of safety situations.
Exactly. Trigonometry helps us analyze and predict, how forces and objects will behave in the real world,
Right.
which is essential for preventing accidents.
All right, folks, brace yourselves because we're about to enter the slightly more challenging realm of quadratic equations.
Oh, yes, quadratic equations. Now, these might look intimidating with their x-squared terms, but they're essential for solving certain types of safety-related problems, especially when we're dealing with, multiple unknowns.
The guide walks through a step-by-step example, emphasizing the importance of the order of operations. PEMDAS strikes again.
PEMDAS is back. It's like building a house. You need a solid foundation to make sure everything else stands up.
Right.
PEMDAS is that foundation for solving quadratic equations accurately.
And these equations aren't just theoretical. They have real-world applications in safety.
They do imagine you're investigating an incident where a piece of equipment malfunctioned.
Okay.
A quadratic equation could help you determine the trajectory of a projectile or the path of a falling object, providing, crucial insights into what went wrong.
It's about using math to reconstruct events and understand the underlying causes of accidents.
Exactly. Quadratic equations give us a really powerful tool for, unraveling those mysteries and preventing similar incidents from happening again.
Okay, before we wrap up this part of our mathematical journey,
Right.
let's give a shout out to our trusty sidekicks, calculators.
Calculators, even seasoned safety professionals rely on calculators to, crunch those numbers efficiently and accurately.
Of course.
But it's important to choose the right calculator for the job and to know how to use it effectively.
The guide actually recommends specific calculator models that are approved for use on certain safety certification exams.
Yeah.
So make sure you familiarize yourself with the functions and limitations of your calculator before you walk into that exam room.
Practice makes perfect. The more comfortable you are with your calculator, the less likely you are to make those errors, especially when you're under pressure.
All right, that was a whirlwind tour of some essential math concepts for safety professionals. I know it was a lot of information, but hopefully you can see how these concepts are more than just abstract formulas.
Yeah.
They're the building blocks for understanding and solving real-world safety challenges.
They are the tools that help us create a safer world for everyone.
We'll be right back after a quick break to dive into some fascinating real-world scenarios where these math concepts have made a difference. Don't go anywhere.
Welcome back to Key Safety Talks. Before the break, we were, getting our brains buzzing with all sorts of math concepts from PEMDAS to quadratic equations, but now it's time to see how those concepts actually play out in real-world safety scenarios. Yeah, let's shift gears and explore some case studies where math was really the key to, understanding what went wrong, preventing future accidents, and ultimately saving lives.
Okay, you mentioned earlier that a tiny error in the order of operations could have huge consequences,
Yeah.
especially when we're talking about structural safety. Are there any particular incidents that come to mind?
Oh, absolutely. There's a tragic case from a few years ago involving a stage collapse at an outdoor concert, and investigators found that a miscalculation in the load-bearing capacity of the stage's support structure was, a major contributing factor, and you guessed it, that miscalculation was traced back to an error in the order of operations.
So someone messed up their PEMDAS, some people paid the price. That's heartbreaking.
It is, and it really highlights the importance of, double-checking our work, using parentheses liberally to clarify the order of operations, and even having a colleague review our calculations, especially when those calculations have, life safety implications.
It's a stark reminder that even seemingly minor math errors can have catastrophic consequences. We need to be vigilant and treat every calculation with the utmost care.
Couldn't agree more. Now, let's shift gears to a different scenario where a misunderstanding of positive and negative values led to a dangerous situation.
Oh, I'm curious. Tell me more.
Okay, so imagine you're working in a chemical processing plant and you're dealing with a tank that contains a volatile liquid under pressure. These tanks are carefully designed with pressure relief valves to prevent overpressurization, which could lead to an explosion.
So those relief valves are like safety valves releasing pressure if it gets too high.
Exactly. But in this particular case, there was a miscommunication about the pressure readings. The pressure gauge was calibrated with 0 at atmospheric pressure, meaning any reading above 0 indicated positive pressure inside the tank. However, the operators were mistakenly interpreting any reading below 0 as negative pressure, thinking it meant the tank was under vacuum.
Oh no, so they were essentially misreading the gauge, not understanding that it was all relative to atmospheric pressure.
Precisely, they thought the tank was at negative pressure when it was actually at positive pressure, just slightly below atmospheric pressure. This led them to inadvertently disable the pressure relief valve, believing it wasn't needed.
So the tank was essentially a ticking time bomb.
Unfortunately, yes, as the temperature inside the tank rose, so did the pressure without the relief valve to vent that excess pressure. The tank eventually ruptured, causing a massive explosion and fire.
Wow, that's a terrifying example of how a simple misunderstanding of positive and negative values can have devastating consequences. It highlights the importance of clear communication, proper training, and ensuring that everyone understands the, reference point for their measurements.
Absolutely. We need to make sure everyone's speaking the same language, mathematically speaking, to prevent these kinds of tragedies.
Okay, let's dive into a case study where exponents played a crucial role in understanding a safety hazard. You mentioned earlier that we often deal with really big or small numbers in safety, and exponents help us wrap our heads around those numbers.
Right. I'm thinking of a case involving radiation exposure. You see, radiation doses are typically measured in units called sieverts or SV, and those doses can range from incredibly tiny amounts to very large and dangerous levels.
So we're talking about the kind of radiation exposure that workers might encounter in nuclear power plants or medical facilities.
Exactly. In this particular case, a group of workers at a research facility were accidentally exposed to a higher dose of radiation than they should have been.
How did that happen?
Well, it turned out that there was a calibration error in the radiation monitoring equipment. The equipment was underreporting the actual radiation levels by a factor of 10.
A factor of 10. So if the equipment read 1 millisievert or MSV, the actual dose was 10 MSV.
That's right, and because the workers were relying on those faulty readings, they didn't realize the extent of their exposure until it was too late.
Wow, so exponents were really the key to understanding the magnitude of that error and the actual risk those workers faced.
Exactly. Without understanding how exponents work, they might have dismissed that factor of 10 as insignificant, not realizing that it represented a tenfold increase in their radiation dose, which could have serious health consequences.
It's a powerful reminder that we need to be comfortable working with exponents, especially when dealing with units that span a wide range of values, like radiation doses or chemical concentrations. A seemingly small exponent can make a huge difference in the real world.
Absolutely. Now let's shift gears to a case study where logarithms played a crucial role in preventing a potential disaster.
Okay, I remember you mentioned that logarithms help us make sense of data that spans a vast range, like the Richter scale for earthquakes or the pH scale for acidity. But how does that translate into a safety context?
Well, think about noise exposure in the workplace. We measure noise levels in decibels, or dB, and the decibel scale is logarithmic. This means that a small increase in decibels actually represents a significant increase in sound intensity.
Right, I remember you saying that a 3 dB increase actually doubles the sound intensity. That's a logarithmic relationship at work.
Exactly, and in this particular case, a safety manager was tasked with assessing noise levels in a factory where workers were operating loud machinery. He took measurements at various locations and found that the average noise level was around 85 djecks.
That's getting pretty close to OSHA's permissible exposure limit of 90 djanks for an 8-hour workday.
Exactly. But here's where the logarithmic nature of the decibel scale comes into play. The safety manager initially thought that reducing the noise level by just a few decibels wouldn't make much of a difference.
Oh no, so he underestimated the impact of those few decibels.
Unfortunately, yes, he didn't fully grasp that logarithmic relationship. Luckily, he consulted with an industrial hygienist who understood that even a small reduction in decibels could significantly reduce the risk of hearing loss for the workers.
So what do they do?
Well, they implemented a combination of engineering controls and administrative controls. They installed noise-absorbing materials on the walls and ceilings, enclosed some of the loudest machines, and implemented a hearing conservation program that included mandatory hearing protection for workers.
And those measures made a big difference thanks to their understanding of logarithms and how they relate to noise exposure. It's a great example of how math can inform practical solutions that protect workers' health.
It is, and it highlights the importance of having a solid grasp of those logarithmic relationships, especially when dealing with hazards like noise or radiation, where even seemingly small changes in the measured values can represent significant changes in the actual risk.
This is fascinating stuff. I'm starting to see how math is woven into the fabric of safety in so many ways.
Me too, and we've still got more fascinating case studies to explore.
Well, we're running out of time for this part of the show, but I'm eager to hear more about how these math concepts have been applied in real-world safety investigations and interventions.
Don't worry, we'll dive into even more captivating case studies in the final part of this episode, so stay tuned.
Welcome back to Key Safety Talks. We went on quite a journey exploring the world of math and how it, intersects with safety.
It really has been an eye-opening exploration of how these mathematical concepts, often perceived as abstract, have very real and sometimes life-saving implications for what we do.
Absolutely. We've covered a lot of ground from the foundational PEMDAS to the slightly more intimidating quadratic equations and logarithms, but
Yeah.
it's all been leading up to this understanding how these concepts have been used to solve real-world safety challenges and prevent accidents.
Right, and we've got some more captivating case studies lined up that I think will really drive that point home.
I'm all ears. Let's dive in.
Okay, remember we were talking about factorials and how they can be used to assess risk in complex systems with multiple components?
Yeah, you mentioned that they help us understand the sheer number of possible combinations of events, which can be crucial for calculating probabilities and anticipating, potential failures.
Exactly, and I came across a really interesting case study involving a chemical processing plant, where a seemingly minor design flaw combined with a series of unfortunate events led to a major incident.
Wow, so it wasn't just one thing that went wrong, but a combination of factors.
Precisely, the investigators actually used factorials to analyze the sequence of events and calculate the probability of that particular combination of failures occurring. It turned out that while each individual failure was relatively unlikely in isolation, the sheer number of possible combinations made the overall scenario much more probable than anyone had anticipated.
So it's like a domino effect where one small failure can trigger a cascade of events.
Exactly, and that's why it's so crucial to consider not just the individual hazards, but also the potential for cascading failures.
Yeah.
Factorials give us a way to quantify those possibilities and to design systems with redundancy and safeguards to prevent those chains of events from leading to a catastrophic outcome.
It's a powerful reminder that safety isn't just about addressing the obvious hazards, but also about anticipating those less obvious combinations of events that could lead to trouble. Factorials provide a framework for thinking about risk in a more comprehensive way.
Absolutely. Now, shifting gears a bit, let's revisit the concept of equation transposition and how it can be used to solve for those critical safety parameters in real-world situations.
Okay, you mentioned earlier that equation transposition is like having a Swiss Army knife of mathematical tools, allowing us to rearrange formulas and extract the information we need.
Right. I'm thinking of a case where a safety engineer was tasked with designing a fall protection system for workers who were constructing a bridge high above a river.
That sounds like a high-stakes situation where precision is paramount.
Absolutely. The engineer needed to determine the minimum braking strength required for the safety harnesses and lanyards to ensure they could withstand the forces involved in a potential fall.
So the engineer had formulas that related the force of a fall to factors like the worker's weight, the distance of the fall, and the deceleration distance provided by the lanyard.
Exactly. But those formulas were initially set up to calculate the force generated in a fall, not the braking strength required for the equipment.
So the engineer needed to rearrange those formulas using equation transposition to solve for the braking strength variable.
Precisely by isolating that braking strength variable in the equation, the engineer could plug in the known values, the worker's weight, the potential fall distance, the desired deceleration distance, and calculate the minimum braking strength required for the safety equipment.
That's amazing. So
Yeah.
equation transposition allowed the engineer to turn those theoretical formulas into practical tools for designing a life-saving safety system.
It did, and it highlights the importance of not just memorizing formulas, but also understanding how to manipulate them to extract the specific information we need in a given situation.
Mhm.
It's about turning those equations into problem-solving tools.
This is really bringing it all together for me. You mentioned earlier that quadratic equations, while seemingly complex, can be used to solve safety-related problems, especially when we have multiple unknowns. Can you give us a real-world example of that?
Sure, imagine you're investigating an incident where a vehicle left the roadway and crashed into a barrier. You might need to use a quadratic equation to determine the vehicle's speed at the time of the crash.
Wow, so we're talking about accident reconstruction here, using math to piece together what happened.
Exactly. By analyzing factors like skid marks, the coefficient of friction of the road surface, and the trajectory of the vehicle, we can set up a quadratic equation that relates those variables to the vehicle's initial speed.
So the unknowns in the quadratic equation would be the components of the vehicle's speed.
Precisely by solving that quadratic equation, we can estimate the vehicle's speed at the time it lost control, providing crucial insights into the cause of the crash. Was the driver speeding? Were there any environmental factors that contributed to the loss of control? The math can help us answer those questions.
That's incredible. It's like using math to become a safety detective, unraveling the mysteries behind accidents and preventing future tragedies.
It is, and every investigation is unique, requiring a different set of mathematical tools and techniques. But the underlying principle is always the same, using math to analyze, understand, and ultimately improve safety.
This has been an absolutely fascinating exploration of how math is woven into the fabric of safety. It's clear that these concepts aren't just abstract formulas, but powerful tools for protecting lives and creating a safer world.
I couldn't agree more. It's been a pleasure sharing these insights with you and our listeners.
And to our listeners, we encourage you to keep those calculators handy, brush up on your math skills, and never underestimate the power of math to make a real difference in the world of safety.
Remember, safety isn't just about following rules and regulations. It's about understanding the principles behind those rules, and math is the language that helps us unlock those principles and apply them to real-world challenges.
That's it for this episode of Key Safety Talks. Thanks for tuning in.